Welcome everybody. You're watching Mr. Fugu Data Science. Thank you to the recent subscribers and viewers. I greatly appreciate it. Today we're doing linear algebra with NumPy, but this is a little different. This is more geared towards people who are doing data science and what I think are useful functions you should be aware of. Feel free to get a hold of me on Instagram and Twitter. For now, all we need is NumPy. Here's the version that I'm using if you care. The first thing, you're going to run into transpose and inverse quite often, so understand what those look like if you're new to linear algebra or a little bit rusty, alright? So here we go. Understand that you're just replacing the columns and putting it into rows if you're flipping it. The inverse is interesting because not every matrix has an inverse. If you have a square matrix, usually it'll be invertible, except that's not always the case. If you have something that has an inverse, your A transpose A always will produce a square matrix, which would be an n by m cross a m by n, resulting in an n by n matrix. If A is full rank, then it will be invertible. I hope that this right here means something to you. It will if you're doing linear regression, for instance. This should look kind of familiar. Nevertheless, this is one practical application that you can use where this right here will turn into the identity matrix. When we're using NumPy, it's kind of straightforward. Look at this for a particular example. Pay attention to the extra brackets that I have surrounding this. This is our original matrix that we're working with. We're transposing it. Here's what we deal with. Here's the original. Here's what it looks like transposed. The only thing that you had to do is the dot capital T. To keep track of what's going on, you could always look at the dimensions and you could take the shape. This is 2 dimensions and it's a 2 by 3 matrix for the original data. Eigenvectors and eigenvalues are always coming up. For instance, if you're messing with singular value decomposition or doing some kind of clustering, things like this, it's really important. So we'll start with this right here, which is ax equals our lambda, which will be your eigenvalue x. The eigenvalue deals with the stretching and the shrinking of a vector of x, alright? If your eigenvalue is 0, then you just receive the null space. We'll end up encountering that today. The determinant is this right here, a minus lambda I. I is your identity matrix, lambda your eigenvalue. We're going to use this example right here. Take the determinant. Notice that on these diagonals, you're going to subtract the lambda, which will be what we're trying to find here. So what you're doing is multiplying this by this, subtracting, then multiply this by this. Expand this out. Then you end up here, get your factors, and this is what you end up with for your eigenvalues. To get your eigenvectors, you will need to set it up the same way, and where you had your eigenvalue that you were trying to find, put it in here. But you're doing this for both of them. So you're doing this for the first one and then for the second one. When the eigenvalue equals 1, we'll end up here. We will solve using Gauss elimination. I'm sure you can use other methods. What we'll do is take this 3 in the second row, change the sign, and multiply it by this top row. Then we're going to multiply this by this, and then do this by this. If you notice here, this is what we end up with. So the vector of 1, 1 will equal 1/3 of vector 1, 2. Understand that this value that you can put in here can be any kind of a multiple value that you decide to pluck out of the air and just put in here. So if we said this is 1, we would say that 1 equals 1/3, and then vector 1, 2 would be 3 times that value. I'm leaving the exact value, which is the representation form here, just so you get an idea. We solve now for the second eigenvalue. Put that in here, end up with this, do the Gauss elimination, and you say, oh no, well this is junk. We got the vector 1 equals 0, and we don't even have a vector 2. Well, dang it. We'll say let the vector 1, 1 equals 0. Now we have no value, so we could just pluck a value and say, okay, we'll say it equals 1. You can see what's going on here, and there's 3 examples I gave links to that you can read and get an idea. It's easy to put this into NumPy, we just use this from the linear algebra, and it'll just be a .eig for your eigenvalues. In your index positions here, this first one's your values, the second one is your vectors. Here's what's printed out for your eigenvalues. Here's your eigenvectors. Notice that we have the 0, we have the 1. The 1 is the v12 that we didn't have, and we decided to dictate it as 1. This is where we have our v11 that was equal to 1/3 of v2, and here's our v2 when lambda it was equal to 1. Something that comes up quite often for checking your balances, basically np dot all close. It returns true if two arrays are element wise equal within some threshold value. And this was set up from an example I saw online, and it's doing a comparison to do your checks and balances basically. We have a Hermitian matrix, and this is interesting because you can find the eigenvalues and vectors, and it's noted by this H. It's actually different because if your conjugate equals your transpose, then you have a Hermitian matrix. For instance, if we have A here and we take the conjugate of it, it means that this negative J becomes positive, this positive becomes negative, this negative J here becomes positive, this becomes negative. You take the transpose of it, and if they both equal, you have a Hermitian. Notice that the results here are not the same with this same matrix we're using. There is a distinction, and there's other eigenvalue functions that you can use within NumPy. I suggest you read the documentation. We can do a trace. Traces come up quite often where you're summing the diagonal portions of your matrix, and that's just np.trace. Let's look at something. I plucked this from Stack Overflow, but it's going to illustrate what we're going to do next. We have this matrix let's set up like this, and what we're trying to do is count everything that's on the diagonal in the yellow. It's set up here with our NumPy array. Pay attention to the brackets. You just throw in your trace and it equals 22. You can do this two additional ways where you call your A trace and then you just call it without a parameter on the inside. So the A trace that I called this NumPy array dot trace. You can also do sum and then the A trace dot diagonal with nothing inside, and it gives you the same thing. You can do something called an off trace, which is taking the diagonal but moving up or down the matrix. For instance, if we were going up to the right one row up, you can just add a 1 with this parameter called offset. If I want to go backwards to the left and down, you just put a -1, and that's going 1 back. I'm sure you could change this up and go up more than 1 or down more than 1, depends on what your needs are. You have the ability to use least squares, which is pretty cool. For instance, if we have a bunch of functions, we already know their coefficients, then we can use this, which is ax equals b, and do a solution and find our residuals. We could find the rank, we could find the singular values, we could find the solution. So here's two examples. If you wanted to click those links and download this code, feel free. We have this array, this A1 that I created, which is a 3x3, and then we have this. So then I use the least squares here and I place in, this is my everything after the equals, and this is the coefficients. This our condition equals none was used because you get this error that comes up that's really annoying. It still prints off your data, but it's extremely annoying, so you can just do this our conditioning equals none to resolve that. And we could print this off, and here's the answers for the 3 particular equations that we had. The residuals on this one doesn't show up because the way that this was conditioned here. If you look at the example for one of these online I provided, it will have one because the way that they set it up. Solving linear systems of equations. And this understands something. A must be a square matrix in full rank. All of its rows must be linearly independent. Also, A should be invertible, non-singular. Basically, its determinant is not 0. Here's the 2 functions that we use. We're setting up this ax equals b once again. Instead of taking the inverse and multiplying it times b, we're going to directly use the solve. And I'll explain why. After this, we put in both of our arrays here. This bottom one B is everything after the equals. We can also solve linear systems with this linear algebra.solve, but there's a few things you need to pay attention to right here. A must be a square and full rank matrix. All of its rows must be linearly independent. A should be invertible, non-singular, and its determinant is non-zero. We have these two functions here. This is the coefficients. This is the everything after the equal sign. You do the solve, and here's what we get. We can also do the same thing with doing the inverse and then the dot product, except there's some issues with that. So let's look into this. When using NumPy, we have two options. The first one above is actually faster and more useful and accurate. We're starting from the AX equals B and going to the A inverse times B. But when you do that, there's issues because one, it's slower. Two, you're making unnecessary computations and excess use of floating point numbers. When you're using the dot solve method, it's actually doing something that's different. It's called a LaPack routine, and it's not actually calculating the inverse. And within it, it's using what's called LU decomposition, and it's using forward and back substitution to solve your problems. The other method, when you do this inverse and then calling the dot product to solve it, it's not fast, and there's issues with accuracy because if A is an ill-conditioned matrix, you're going to have some issues. But here's how you would solve the same problem. In this case, we get the same answer if I'm not mistaken, but just be aware that there's issues. NumPy allows us to do multiple linear regression as well, which is pretty cool. So I hope you noticed this if you watch any of my previous videos, or if you've ever seen linear regression. Here we go in the matrix form where you can solve for your beta, and if you were to do this by hand, it would look just like this, for instance. And if you click this link, you could see the expanded form where they fulfill the whole linear regression task instead of just finding your betas. They do the whole rundown in this example. We have different forms of matrix multiplication, which is pretty useful. For instance, you could have this A and this B where you have a 3x4 and a 3x3, and depending on the way that you set it up, you're going to end up with different results because the order does matter. NP.multiply is an element-wise multiplication. And there's something interesting here. You have a 4x3 because we had to transpose this A, multiply it by this B. But that gives you an issue. And we have to do something that you may have seen or may not have seen. Your matrix, and then you call the bracket, call all rows, comma, and then for your columns, you're changing the columns to saying NP.newAxis, and then you're still transposing this. And it'll do the multiplication for every single element that's in these. So you got to be aware of this. If you rotate this and do B times the A transpose with all of that, it gives the same thing for this. But let's pay attention. If you're taking the same thing that we just had above, but you're doing this new one, which is MAT-MUL, matrix multiplication, it's not doing the same thing. It's quite different, because what would happen is you're taking this 1, multiplying it by this 2, plus you're doing this 5 times this 4 equals this 20. 9 times 6. 54. And then if you did the same thing with the 1 and the 8 equals 8. 5 and the 10 equals 50. 9 and the 12 equals 108. Then you do the same thing with this one and go through this one. And then you keep moving over to fill up the rest of this. That's what's going on with this one right here. We could do a dot product in two different ways, NP dot and then AB, or A dot B. Either way, it's the same. This is going to be different than what you're going to see in the next one. So please pay attention. We'll take this and return a scalar. We're doing 2 times the 7 plus the 3 times the 9. So this row by this column, this row by this column, this by this by this, and repeat that. And here's the two forms of doing the same thing. We could do an inner product, which returns a scalar, and this is a little bit different because you have 2 times the 7, then you have the 3 times the 8. So we're going row and row. The other one we did row and column, okay? That's a distinction. You got the cross product, we could do it two separate ways here, and this is what it looks like, and you just chuck in your A and your B, and here's your result, which is a vector. You got to notice that there's cases where you get an error, which you'll need to do a transpose, and it's because it's implicitly looking for a horizontal vector for its assumption. You have an outer product where you would take this U1, multiply it by V1, U1 by V2, U1 by Vn, and you go across. then you go to this next one and you do the same thing. And here's your outer product, okay? So that's the end of this video, but don't forget we have the gradient and SVD as well that are very important, but I didn't cover in this video. But please like, share, and subscribe. And if you subscribe, turn on that notification bell. I did this as a primer to help you out as an aid, but I hope this really brought utility to someone. Feel free, if you can, to help support this channel and buy me a coffee, and there's my handle. Feel free to go on my Twitter and Instagram and hit me up. See you in the next video. Bye.